Hello everyone. This video is about the use of Maxwell equations to derive the speed of light. Uh, so to begin with, let's take a look what we have learned from Maxwell equation. We have learned this equation, divergence of E being equal to rho divided by epsilon. And we have also learned the curl of E is equal to del V del T. And we have also learned the divergence of B is always zero, and there is no magnetic monopole. And we have also learned curl of B is equals to mu and then J plus epsilon and then del V over del T. So the first Maxwell equation here is the product of Gauss's law. And the second one, right, the curl of E is V the flux divided by dt. This one came from Faraday's law. And divergence of B is zero. This one is another version of Gauss's law applied to magnetic field. And what it means is there is no such thing as magnetic monopole. The last equation is more complicated. Maxwell initially had this equation, which is the product of Ampere's law. But then he found out there is some issue with this equation. He believed magnetic field, change of magnetic field in the space can also generate, change of electric field in the space can also generate magnetic field. So he add one more term here. And this terms is this one. And he believed this is so-called displacement current. So this displacement current is not due to the movement of the electric charge. So in other words, the last equation here is due to Ampere's law and Maxwell's displacement current. So we have 1, 2, and 3. Let's label them first. Now we are going to use these four equations to derive the speed of light. And before going forward, let's assume that the space that we are dealing with is totally neutral. Neutral in the sense that there shouldn't be any net charges. Net charge, the no plus charge or minus charge. So in other words, rho here is the charge density. To begin with, the charge density should be zero. And by the same tokens, with low charges at all, there shouldn't be any current. dq dt is zero. So this one is another term to be cancelled. So this is the assumption we have. Now, we are going to use this equation together with our assumption to derive the speed of light. The first step that you should do is to take curl of equation 2. So we will take curl on the left side. We end up with this equation, this expression. And if you take curl on the right side of equation 2, you have this one here. And we can apply some vector calculus identity to simplify the equation. The left side of this equation can be simplified into this one, and then minus Laplacian of E. And the right side of the equation, say this is equation 5. The right side of equation 5 can be written as, we have this term here, we can differentiate this expression first and then take curl. Now, we can make use of our assumption, our initial assumption, to simplify this equation. First, divergence of E. We have already assumed that the space that we are dealing with is totally neutral. There should not be any net charge. So in other words, using the first equation here, divergence of E is 0. So we have 0 here, and we have what we have left is this one. And now the right-hand side of equation 5 can be written as del T, and then what is curl of B? According to here, it is mu epsilon and then del E d over dt. So in other words, you can simplify the right-hand side of this equation. And then with the second time derivative of E. Okay, the right side can remain as it is. And the minus signs in both sides of the equation can be cancelled off with each other. So this is the equation that we are going to play with. This is the very famous wave equation. Wave equation. And now the wave equation can be further simplified as well. For those who are not familiar with the wave equation, then pay attention to what I'm going to do here. So I'm going to simplify this wave equation. So for the time being, let's focus on the x direction only. Let's focus on x direction only. So in other words, the left-hand side of this wave equation will be written as del e del x. The right side of the equation can remain as it is. So we are going to simplify this equation. So this is equation 6, the wave equation. Let's start from the left-hand side only. The left-hand side is this one, the Laplacian of the electric field E. Now, what it means is you can say, you can rewrite this expression as this one. And now, what is del x, right? The inside the bracket, we can rewrite dE by dt, dE by dx as we can do that. So what is del t divided by del x? It's actually, if you have done calculus, you know that velocity is equals to del x over del t. So if you have 1 over del x, if you have 1 over del x, right, you know that this one is actually 1 over v. So we can rewrite this. Now we have another del x here. We can also use the same treatment as we did for del E over del x. This del x can be written as we can do that. So del T on the top and del T on the bottom can cancel out with each other, leaving only del x at the bottom. But now we are now trying to simplify this expression. Now, again, del T over del x is 1 over v. So what we have here is 1 over v square, yeah? And then del E. I don't have enough space here. So let's Let's free up some space on the right box. So let's continue. We have this expression, and this one is actually 1 over v squared, and this one here is del e square, del t square. So the second time derivative of the attribute. Now, this is the derivation based on the expression of the left side of equation 6. So if the equation is an equation, the left and right have to be equal. The left now is proven to be equal to 1 over v squared, and then times del e squared or del t squared. So if they are equal, this means this expression here has to be equal to this one. So let's write this down. 1 over del e squared, del t squared. And the right side of the equation, both sides of the equation have the second time derivative of e. So they can be cancelled off with each other. So what we have left here is 1 over v squared equal to mu, the product of mu epsilon. So in other words, the speed of light can be written as 1 over square root of mu epsilon. Mu is the permittivity. Sorry, mu is the permeability, the magnetic permeability, and epsilon is the permittivity. So different space will have different value of mu and epsilon. For instance, if you are dealing with free space, mu is equal to mu naught. Mu naught is equal to 4 pi times 10 to the minus 7. And epsilon is equal to epsilon naught, which is equal to 8.845 times 10 to the minus 12. So together, if we substitute mu naught and epsilon back to this equation, say equation 7, we will get V is equal to 2.998 times 10 to the power 8. So which is almost the same as the speed of light. Speed of light in free space. And of course, if you use the same principle to derive the speed of light in water, you can also do that. In this case, epsilon is about 80 times epsilon naught. So you will get another speed of light here. Different material have different speed of light. If you have any question, please leave your questions to the comment section of this video. Thank you. Bye-bye.